In this video, we're going to go through the basics of curves in the plane and one-forms, things like this, and we're going to show how to integrate one-forms over a curve. A curve for us will always be a parametrized curve, which initially we define as a continuous function gamma from an interval into the complex plane, and the starting point will be gamma of A, and the final or ending point will be gamma of B. And so a parametrized curve is just what you're used to from calculus. We're mapping the interval A, B into the plane, and you get some sort of path that starts at gamma of A and ends at gamma of B. But we don't want it is a parametrized curve, but we don't want it to depend too much on the parameterization. So we'll say that two curves, gamma 1 and gamma 2, defined on possibly different closed intervals are considered equivalent if you can go between them with a continuous invertible map. So there exists a phi from the interval AB to the interval CD that's continuous, invertible with continuous inverse that comes for free, but might as well state it. That preserves the order of the curves, so it doesn't, make the curve go into an opposite direction. Phi of A maps to C and phi of B maps to D, such that gamma 1 is this composition of gamma 2 and phi. So the phi is just taking care of kind of different speeds in some sense of parametrizing the curve, but it doesn't really change the set that you map to or its direction. Here are a couple quick, very basic examples. So we can take the line segment from a point z0 to z1. So just the straight line segment between them. And we'll write it with this interval notation, and that's usually pretty convenient. And I can parameterize it using the interval 0, 1, and I'll just write gamma of t is 1 minus t times z0 plus t times z1. And so it starts at z0 because I get gamma of 0 is z0 and gamma of 1 is z1. And it's definitely a straight line. Okay, then another basic example might be a half circle. So the counterclockwise half circle, half unit circle, I should say, from 1 to minus 1 will go this way, and it can be parameterized with e to the it, where I have t going from 0 to pi, or I could parameterize it this way with sigma. And this is a little more complicated, but maybe it doesn't use transcendental functions like e's. So minus t plus I times square root of 1 minus t squared. So they both do what we want. So I have gamma of 0 is 1 and sigma. So sigma here starts at minus 1 and goes to 1. So they're parameterized on different intervals. But sigma of minus 1 maps to 1 as well. And they have the same endpoints. So gamma of pi gives me minus 1. Sigma of 1 gives me minus 1. And then if you were really interested in the details, you could check that these were actually equivalent. We won't go through that, but maybe just leave it as an exercise. We also have a related notion. Curves that have the same starting and ending point, we'll just call it a loop or a closed curve. And we also want to consider loops equivalent to sort of shifting of the starting point, because a loop will be a curve that joins up on itself, and there's nothing really special about the starting point now because it's a loop. So we want to consider it the same loop if I start somewhere else. So that's what this definition is saying. We consider gamma equivalent to gamma tilde, and this is just some way of kind of starting at a different point. So I put in gamma A plus delta to B plus delta, and gamma tilde will be equal to gamma of t when I'm in the original interval in question. And then I just have some kind of trick to parameterize the rest of the loop using the remainder of this interval. I haven't changed the length of it. But so we'll consider our original loop equivalent to this one in some sense, and we'll also maintain the earlier equivalence. So if you reparameterize or shift the starting point, you'll consider them the same object. And so here's a very basic example of a closed curve, just the circle of radius r centered at 0. I can parameterize it with r e to the I theta going from 0 to 2 pi, or I could parameterize it going from a to 2 pi plus a for any real number a, and I'll consider them the same object. We also need the notion of the reverse of a curve. So if I have a curve here, then minus a is just going to be the curve that goes in the opposite order. So it's just the curve that follows the same set, but it starts out at the end point of gamma and ends at the beginning point of gamma. And this is just some formula that gives us the right thing. I think if you check here that when I plug in A, I get B, and when I plug in B, I get A. And so this is if I have a curve gamma. Parametrizing a curve basically just gives it a direction. And so minus gamma just goes the opposite way. So these are all the very basic notions related to continuous curves in the plane. And now let's get into one-forms and how we can integrate a one-form over a curve.